Gonna go ahead and start because I think I have a limited amount of time. I got 12:56 according to my computer clock. So let's get going. My name is Jimmy Newland, and I teach computer science um, from time to time. And I study computer science and physics education. But my main gig is a physics and astronomy teacher. Now, I am a computer science guy. I'm going to try to make that claim as we move on. Hopefully, I'll prove it to you. And I'm going to talk about how I have tried this year, this nightmarish school year, to use coding in my astronomy class in a remote sense. And I'm also going to talk about how physics education in general, because astronomy is often considered part of physics education, how exactly is physics education using computing? And before I go to the next slide, well, I should probably also share that I'm a member of the CSTA chapter in Houston. So shout out to all my Houston peeps if you're listening to this after the fact. Thank you, Shayna, for making sure Houston was represented at this Texas CSTA virtual conference, and that's super cool. But when I moved from computer science teacher, here, I'll go to the next slide now. I'm going to try anyway. As I moved from computer science teacher to science teacher, the bizarre thing that happened to me is I realized how little the two areas overlapped. And I found it very frustrating. So, who the heck am I? Why is this physics nerd talking about computer science? Well, I got my bachelor's degree in physics and astronomy. I wanted to go to graduate school and study some sort of astrophysics. So I tried that out. I was at University of Houston for a year in Dr. Edgar Baring's space physics lab, the plasma physics studies of the upper atmosphere. And it was just not the right time for me to be a researcher. Long TLDR spoilers. I'm back to being a researcher, but I moved from UH's physics department, where I was a graduate student. I moved into the College of Education. I got a master's in education in science ed in the curriculum and instruction department, and from there, I just checking the chat, make sure I'm not missing anything. I heard about an opportunity to work at Beller High School in Houston, Texas. So I showed up with my computer terms, like some, I heard that it was a computer science job, but I'm thinking to myself, uh, maybe there's something I can do. So I show up. My resume says that I have some computing experience, and they're like, well, I don't know, physics nerd. And so we talked a little bit, and I decided to give it a try. They hired me to teach computer math, which was basic back in the day. For those of you out there who remember the days, the 90s, of the computer math class in Texas, I taught basic, but I also taught AP Computer Science A, and I taught AP Computer Science AB. Sometimes one, sometimes the other, sometimes both. So I've taught Pascal, I've taught C++, I've taught Java, and I did that for a long time. But along the way, I also did a web design course. I taught HTML, I taught PHP, so web programming. And again, if anybody's here with me, I don't mind really doing this into the void. That's how school has been anyway. So it's not going to change anything. But if you are, feel free to drop in the chat and say something to me, so I know that you're there and that you have a question. I don't mind being interrupted. I am a teacher, so interact is good. Anyway, so I did web design class over the years. I've done IB Computer Science, the International Baccalaureate Computer Science class. I used Java to do that, and I even taught for 1 year a introductory computer science class using the language Scheme. And I used Rice University's Dr. Scheme platform, and I used the How to Design Programs textbook. So I did that for a full year. But at the end of that year, I actually got an opportunity to teach physics and to teach astronomy. So I moved out of computer science. Now, I still taught a class here and there, but where I am now, I'm teaching physics and I'm teaching astronomy. And my interest in computer science really started to, I just was curious why the computer science learning techniques that I've seen, why weren't they showing up when I went to professional developments as I started to do my own dabbling in astronomical research? Why was the computing education bit so lacking? So I am at University of Houston. I'm in my second year of a PhD program. I'm trying to look at how computer science pedagogy and physics pedagogy are both complementary and in each other's way. So my general research topic, and I have other research areas, but today I'm going to focus on how can computer science pedagogy support science learning, and specifically I'm going to talk about physics and I'm going to talk about astronomy. Okay. I'm just checking the chat to make sure I'm not missing anything, so forgive me as I dabble back and forth there. So I feel like I need to tell you what computer science means to teaching science classes. And I'm going to use the term computational thinking. It's been used a whole lot. It's part of the the next generation science standard. So it's there. Hang on, I see in the chat. I don't want to miss anything. Because I'm noticing that there's a dearth of individuals, and I want to make sure I'm not in the wrong place. I hope not. As people are looking at this, future me. There is a poll, by the way, where I asked, have you ever used computational thinking in a science class as a learner? So even if you don't quite, pick one. Yes, no, I don't know. Anyway, so what do I mean by computational thinking? Well, it's got four real strands. There's the data practices branch. There's the modeling and simulation practices, there's computational problem solving, and there's systems thinking. So the first one, data practices, this is, interestingly enough, really not just science, not just computer science, not just math, but this is something that could show up in social science courses as well. Collecting data, manipulating it, analyzing it, visualizing it. It's a complicated reality, but surely anybody watching this is going to acknowledge that if you're doing work in the modern world, there's data, and being able to handle it, manipulate it, and know what's going on with it, that is a data practice, and it's part of the computational thinking structure here. So it's really definitely room for computing, especially when it comes to using code to do these things, outside of the data practices being for computing. It can be anywhere. So often when physics teachers discuss computational thinking, they're really referring to modeling and simulation. And there's a lot to that, and I'm going to talk about that specifically, designing models, but actually using models to learn science. So not just the idea of simulations, which is definitely a part of teaching science, but also using, computing ideas, like coding ideas, to test simulations and test your ideas on simulations and that sort of thing. I'm noticing I'm getting some notifications here from some people trying to attend. So I'm just going to try to do that while I talk. The third one there is really the computational problem solving one. That's the one that comp sci people are often doing. If you're doing comp sci, you're doing programming. And it's probable that this is the one that's missing the most from science classes. I'm going to talk about that in just a minute. Hang on, talking to someone on the chat who's trying to get in my conference, but they're at the Digital Divas conference. So let me just do that real quick, and I apologize for those of you who are here. Cool. All right, so the third one though is really computer science centric. It's programming, it's assessing whether or not an algorithm works, it's the abstractions idea, it's debugging. That's computer science, like computer science A. Not so much computer science principles, which really sort of leans on all four of these, AP computer science principles, I mean, but the AP computer science A course is that third row. Then there's the systems thinking practices, which shows up in a lot of sciences, but in physics, it might be something like, where are the edges of my system? I've got a car on a table. Do I need to worry about friction? Is gravity important? So thinking about relationships, thinking about the levels, like how big do I make my system? How small do I make it? And all of these, by the way, are borrowed from Weintraub et al. And I would just make the point that Weintraub is an active member of Weintraub is not the only person who's saying this sort of stuff, but an active member of the committee at AAPT, the American Association of Physics Teachers. They're trying to nail down what computational thinking means in physics classes. And before I move on, I think I should probably mention here that the central idea of what I'm doing is kind of exemplified by Orban and Teeling-Smith, who have a paper from 2018 where they talk about coding in physics classes. And they said introducing computation into high school or college non-major physics courses should not be done solely to provide an early start to the kind of skills students need to be a professional physicist or a software engineer. Now, I hear this kind of talk in CS education all the time, that computation is not just for people who want to work for Amazon or want to do data science professionally. It has a role to play in all learning. Computing is for everyone, I would simply say. My goal here is not necessarily to make the students in my introductory astronomy class ready to go work for just again, people trying to get in here. I think the Digital Divas conference goers, I have a couple of friends who are there, can't come to the conference for CSTA, and I think there's a little confusion there. So I'm just letting her know that. Okay, sorry about that delay there. So anyway, that's a big theme for me. It's not just to make you a future, job in computer science, but science and computing can help each other out. Okay, so I'm going to specifically talk about some modeling related things, and I'm going to focus on that because it's when people think physics and computing, they often think about something called Euler-Kromer. So what in the heck is Euler-Kromer? So if you're familiar with the mathematician Euler, well, then that's not surprising. But you may not know this sort of modern physics scholar Kromer, who tried to take Euler's idea of taking a function, and you don't know what it's going to do, in some particular little area. You don't know what it'll do way later on. You don't know what the function did way long time ago, but you're only interested in what it's doing at the bit right in front of you. So this is very common in computing, and we often use iteration to handle the Euler-Kromer way of doing physical modeling of things. Video games use this a lot. It's used all over physics, computational physics work. So what's going on? If you look at this chunk of code from this is P5.js that you see on the left-hand side. It is a web-based language that is heavily used in again, do I have anybody in my talk? Okay, that's okay. I don't. It's lonely. Anyway, P5.js is a web-based JavaScript implementation of processing that is used for arts, computer science work, and Orban and Teeling-Smith have started a program called STEM coding, where physics teachers can teach physics using coding. And this is I took a class from AAPT. I went to the professional developments, and this is it. One of my labs. It's not great, but it's there. And so what's going on? So I'm gonna actually play this video. Hang on, get it to play so we can see it. There's a circle there. Dr. Orban calls that a blob. So let's move the blob. So 1 and 2 here, where the blob located. So where is it in my screen? And so I would mention that they've gone out of their way to make the origin work like a Cartesian coordinate plane and not the sort of canvas coordinate system that we often see in computing, where you have to start 0, 0 at the top left. The developers of this, Orban and Teeling-Smith, have tried to make the origin where you would expect them at the bottom left. Anyway, so move the blob. Where is it located? What's its speed? How fast is it moving in the X direction? How fast is it moving in the Y direction? A common phrase you might have heard if you've taken a physics class. And line 7 is really important here. Line 7 says, what is the tiny little time interval? So as I'm trying to advance my simulation, by how much time will I advance it? And that's its own interesting thing to dig into. But here it's zero point 0.1 time units. Okay, so what does that actually mean? If you look at lines 9 through 20, this is a function called draw. And if you're familiar with P5JS, you might already know that there's built in to P5JS is this automatic iteration. So the anytime you use the draw or anything you put in the draw function, P5JS is going to run it as many times per second as your browser can get away with. Well, I think it's up to 30 times per second. And I'm not even sure if one can control that. I guess it depends on circumstances for your server and stuff like that. But it's doing it lots of times per second. So what it's doing is wherever it will look at line 12, wherever it was a moment ago, move it to a new position based on the speed and the time that's passed. So that 0.1. So move it there. That's where it's going. And for those of you who've done comp sci before, you recognize that strange, update the data on the right-hand side and store it on the left. So this is immediately something that students are going to have to address. Like that is not an algebraic statement. And then there's a couple of other lines here that are kind of maybe not very clear, but they're not really necessary. The student is given some sort of direction on what's going on there. Hey, it's displaying. Hey, it's drawing the blob. But they're actually only going to play around with this. So Euler-Kromer modeling is the idea that you use well-known equations here. I'm using one of the kinematics equations, and we update the position or the velocity or the acceleration by doing iteration. And it's extremely common. The question is how much computer science content knowledge is really required, and that really varies. So there are really 3 models for this. And I would tell you that the first one over here, when I was a graduate student, well, also an undergraduate physics major, the idea for this first column, traditional computational physics, I mean, this is coding. This is straight up coding. You better know how C or Java or Fortran, you better know how the language handles for loops and or iteration in general, and how you handle data, and what kind of is there object-oriented programming. If you're doing C, you better be ready to handle the references, pointers, excuse me, sorry, a little Java speak there. So this is really meant for someone who is in the major for physics or astronomy or bio or chemistry. It's a major specific kind of thing, and it's prepping you to be a professional physicist. And it's heavy duty. It's a lot of computational pedagogy needed. Now, on the far right is something that I would describe as the, again, I'm getting notes over here. Yeah, people reaching out. I think I'm not the only one alone in their session, but I'm okay. That's okay. This far right side is what's known as the PhET, or the Physlit approach, black box simulations. And if you've taken a computer science class, I'm sorry, if you've taken a physics class, you probably used a PhET, or if you're a physics teacher, or maybe you've seen it in a training, they're black boxes. And so some programmer has designed the simulation to let the learner interact with, say, electricity and magnetism, or gravity, or friction. And whatever pedagogical sort of outcome you want, you've got to have coded it into the black box. Now it's got iteration built in, it's got, setting up the initial conditions and changing things around. It's got built-in visualization. And I cannot stress enough how important the PhET ecosystem is to teaching physics. But it's really lacking in, so there's computational thinking, no doubt, but there's no coding. So there's this middle way. This is where I would point you to Orban and Teeling-Smith's current work. And they're not the only ones. Let's Code Physics, Dr. Brian Lane, and Adam Lamy working in Florida. Actually, so is Dr. Lane. And there are others out there. So this hybrid approach of can we maybe take some of the computer science load, off the shoulders of the student, but let the code still be a little bit hands-on. So they are setting the initial conditions, they're iterating, some control, as opposed to maybe worrying about the syntax of your language. So often in this hybrid area, someone's written a system that allows for taking off having to learn Java or Python or C. God forbid you have to learn C. So this hybrid approach. So that's where I'm coming from. I want to use Euler Cromer to a certain degree, but my thinking is really centered on the center column here. All right. So how does that work? Again, if anybody's in here, take my poll, drop something in the chat, talk to me, because I'm not, I'm talking over here. I don't want to miss something. So please. So I really, we can't talk about science and computing without discussing how this ecosystem has grown over the last 20 years, starting with the Matter and Interactions textbook and curriculum, which uses VPython. It's been growing and it's still going. You can see the web-based VPython GlowScript environment there from their website, from the Matter and Interactions website. This is, if anybody's familiar with this textbook already, it's by Sherwood and Chabay. And I think it's Chabay and not Chabay, Chabay. The idea here is that you take an introductory physics class and you do, a question about the net force on an object isn't answered with paper and pencil and algebra, but instead you write a chunk of code. So again, this is a version of Python that's been manipulated to reduce some of the cognitive load. The students can handle vectors quickly and velocity changes quickly, but you're still doing some coding. So it's definitely that middle approach, the hybrid. And this is quite old for a computing platform. Matter and Interaction has been around for a couple of decades. Then there's the cutting edge here, the from the world of Lisp and Scheme and Racket. There is a thriving, but maybe still kind of in alpha mode, if I can use computing lingo here, not quite in beta testing mode, something called Pirate from Bootstrap Physics. And they are working with the people who are very good at functional programming in an educational context. So those people that have done Scheme for teaching computer science, for example, or Racket for teaching computer science, they're trying to develop a series of curricular tools, a curriculum for teaching physics and math using Pirate. And you, hopefully, if you're familiar with Scheme and Racket and the Lisp world, you recognize the red and blue, color scheme and the lambda made out of the skull and bones. It's a sort of a take on Python forced to do the world of contracts and what does it consume, what does it return. And I would point out that the Matter and Interactions has been around for a long time, but where this guy's not, they're not ready for prime time yet. Pirate's not, but there are a couple of other options out there. First of all, there's Dr. Brian Lane's YouTube channel called Let's Code Physics, with a wide variety of ready-to-go examples, ready for high school, ready for college, for doing using Python. You can see Trinket here in this screenshot from the YouTube video, so you can tell it's web-based, but it can use VPython already. It's ready to go. You don't have to write the traditional Python with a lot of that overhead. It can use VPython. So this is a sort of a Matter and Interactions methodology. And Dr. Lane is active on Twitter, and his YouTube channel has lots and lots of folks. So I put a link to it there, and a link to one of the Trinket segments from, blocks from his course. And then I put my mouse is over the link, but I put a link to where his actual problem sets are located. And I honestly can't say enough good stuff about STEM coding. I've reached out to these folks and I'm like, look, y'all, I am new to this teaching with coding, and I am an educator trying to study this. And Dr. Orban has been insanely helpful. Meets with me often over Zoom to work on my research questions. So I really have a lot of positive interactions with the STEM coding world. It's been interesting to use P5.js instead of Python or Java or something else. And the way that processing was designed for teaching computing, and also that P5.js has been leveraged for using art in computing, really it's something you should investigate if you're a computer science educator, how this works. So links to their stuff there, and you can see one of the samples from I would not call it asteroids because I don't want Atari to sue STEM coding, but it's an asteroids-like game that students actually code. In fact, I would probably be remiss if I didn't point out that Orban and Teeling-Smith have the attitude that students not only doing physics with coding, but making games as they do, makes it more entertaining and more fun. And I would say that that's absolutely true. I would also point out, I guess I should have said this earlier, but I think I was more concerned no one's in my room with me. But it's this entire movement of making the hybrid approach. Why aren't there more people of color in physics classes? And how can equity in science education be addressed through using coding? That's actually, even though I didn't explicitly say that yet, that is definitely part of it. And I would like to point out that that's something that the STEM coding folks are constantly talking about, addressing equity, gender equity, and race equity in physics education. And I would also say that what I've seen of Let's Code Physics and Dr. Lane on social media is the same kind of thing, trying to be a part of the conversation on equity by addressing science education through computer science. What an interesting take on things. So there are other games in town. I feel like we should mention them because I certainly use Desmos a lot. I'm still playing around with Tychos, but I decided to throw these in here because if you're a physics teacher or a math teacher, you've probably heard of Desmos. Desmos has so many little ways in which computational thinking is a part of the calculator. Therefore, when you use it in your class, you're using computational thinking. So data practices, and certainly iteration is built into it. You can do linear regression, which I guess I didn't do in this example, but I use that a lot in my AP physics class. And on the right-hand side is Tychos, which is, again, sort of in, alpha mode, I would probably say. It's the Euler-Kromer modeling, ECM modeling. It's all in a browser, and they've reduced the cognitive load even more, I would say. So not quite the same as VPython even. So they've sort of taken the look and feel and the behavior that you see when you interact with Desmos, and they're trying to bring the coding part of computational thinking to it. Desmos may go down that road as well, but right now the computation layer is really only available to the educators, to the teachers. So Tychos is kind of a new game in town. I'd like to see if they get a lot of followers and get some development. Both of these are free to educators. As a matter of fact, everything I've shown you so far has been, the material is widely available for free, usually on the web somehow or another. So I also wanted to talk about physical computing a little bit because it's something I use. I don't use it in astronomy education, but I am still planning on trying to do some physical computing during virtual learning. So I have a bunch of Arduinos, and I think I'll make some kits, put them in a Ziploc, and wait outside my school with a mask on and have students come get them from me. So we're going to try to do physical computing remotely. So it's a place where, obviously, if you're familiar with physical computing in any way, you know that it's project-based learning, it's hands-on, it's very constructivist. You've got that inquiry model, and I have 3 different lessons here that I've done, including the Visualize Your Heartbeat Maker Challenge, which I wrote in conjunction with today's working with today's keynote speaker, Alan Antoine, at the Rice University RET Research Experience for Teachers. And I actually did this lesson where physics students measured their heartbeat and analyzed the signal using code and Excel. And in the middle there is the very traditional RC circuit lab where students gather data using an Arduino on how long it takes an RC circuit to charge or discharge. And on the far right-hand side is actually another Rice University project that I was associated. Again, Alan Antoine is showing up, using a microbit to emulate a traffic light. And hopefully you can tell that I'm using MicroPython. You could definitely use block-based here, but I'm using the MicroPython because I thought it was kind of cool. So these, physical computing is definitely part of the game as well. It's part of the ecosystem of coding in your science classes. But I really wanted to talk about how we could leverage computer science pedagogy. And specifically, I'm talking about cognitive load theory. So I got Morrison et al. Saying that cognitive load theory suggests that new learners can't handle so much syntax, and it gets in the way of them learning. If you were interested in them learning iteration, but they aren't good at the syntax, well, they can't get there. And then again, Morrison and Margaloo from 2015. So how do we, mitigate this? And sub-goal labeling, which actually comes out of psychology research, and worked examples, which both of them are used in math education all the time. And it turns out that if you can, like you can see my example here, I have comments, I have when these are from a couple of my labs, I've given the students some examples, like how do I use this? What do I do? So trying to make the syntax and the how does the language do what it does not get in your way. So reducing the cognitive load. So that's what I believe is going to be the answer. It's certainly proving to be true in math education, and it's certainly proving to be true in computer science education. So if we're going to leverage coding in our science classes, we need to learn the lessons or use the lessons that are already learned. That you need to be aware that coding in a science context can get in the way. So how did I try to find that middle way, that hybrid approach, by using this notion? So I know it seems like a weird, like a segue here to have a little bit about a computational essay. It seems a little strange, but I promise to make it make sense. So you've probably heard of Wolfram Alpha or Mathematica. Stephen Wolfram owns Wolfram Research, founded Wolfram Research. He's a PhD physicist, but he entered the tech world back in the 90s. Wolfram Alpha is, of course, an ongoing sort of artificial intelligence live experiment. Well, he wrote something in 2017 called Why the Computational Essay is a Great Way to Communicate. And it has live code and it's got text. And I have a link to it there. And he puts his money where his mouth is and talks about the computational essay in a computational essay. So it's a web page where code can run live. So anybody who's familiar with Jupyter Notebook should recognize that there is the capacity for doing that very thing, for doing computational thinking, having students do extended writing, having students doing coding together. So I saw Odin speak about this at AAPT, and this image is from Odin and Burke's 2020 paper from late 2020 about how they're using computational essays in physics major courses. So students starting from scratch have a problem-based learning kind of mentality. It's their research class. The student picks a topic, they dig into it. They, extended writing about how the process goes, extended writing about how they're modeling, extended writing about how the data collection goes. You can include images, you can include latex. So, graphically displaying, and I want to say it one more time, just in case anybody's here. Be sure to, if you're in the session with me, drop something in the chat. Let me know if I need to answer your questions, because I really want to do that. Anyway, so this is from their paper, but I thought to myself, well, can I use this without it being something the students write all themselves? How can I maybe start the computational essay model, almost like using the worked example idea heavily? How can I use that to do labs? Well, then I came across Adam Lamy's work at codingink12.org, and that was exactly what he was doing. He had these Google Colab, so Jupyter Notebook, but running in the browser. He had these Google Colab exercises where students were expected to, read the extended writing, write the code, play with the code, interact with the code, and ultimately, save it and then turn it in to be graded. And I decided to add one more layer and have the students not just running and adding code, but maybe, let's put some open-ended questions in there and do some inquiry-based writing. So, but I have to admit that after I saw Adam Lamy's work, I'm like, this is what I've been wanting. So thank you, Mr. Lamy, and thank you, Dr. Odin and Dr. Burke, for your work. So what did I actually do? How did I do this? Now, first of all, I would like to say that this is an experiment in progress. I did a lab for my physics C students using Kepler's third law. I don't have a lot of feedback from it other than the students completed it. I do have a little bit of analysis on one of the astronomy labs I'll share with you in a minute, but I need to tell you what I've decided to do. And again, this is like a live experiment. So I had the cognitive load theory in my mind, realizing that computer science education has something to give science education. And I tried to take Lami's example and Odin's example and merge them together. Sort of let the students write some, let the students type some code. It all runs in a web-based platform. So this works for asynchronous. It can be done with remote group work or individual work. I would prefer them to do group work, but if you're a teacher in this hellscape that is the pandemic, you're probably aware that you can say you wanted to do group work and they may end up doing it right before it's due, at the last minute on their own. But nonetheless, that's an aside. So I have an example here from one of my labs where astronomy students are trying to measure the amount of europium in the stellar spectrum of a star, or 5 different stars. And on the left is like a screenshot. There's a link to this Google Colab in a moment. I just want to say a little bit more about Google Colab before I move on. I want to make sure I get to the end here, but it's important to note. This is Python. It's Jupyter Notebook, but Google has made this web-based. So it uses Google Drive. It uses Markdown, if you're familiar, so you can write HTML and LaTeX, and you can also write code that it will run one block at a time. So I thought to myself, now that I'm here, let's make this real. So luckily, I've had an opportunity to work with some professional astronomers in my time. And I asked them, like, how do you do visualizations? What sort of algorithms do y'all use? How do you do this, that, and the other with data sets? And I thought, I'm going to bring in real data sets and we're going to do some real algorithm stuff. And often I'm doing the scaffolding for them. So the students aren't necessarily, doing like a min-max algorithm to find the brightest quasar in a pile, even though, we might get there, but they're still interacting with it. They're seeing it. Besides, if you're looking at a black box simulation, they don't know how anything is working. So the notion here that they can use the code, can alter the code, can play with it, they can poke it and prod it and see what things do. But not only that, but I explain it. Like, this algorithm does this line does that. And I ask them to, in the center image, this is from the lab. They were supposed to have generated the red one, the orange one, the purple one, the blue one, and the green one. And then answer some questions about the plot they made, what it must mean. So I'm trying to use authentic, actual, astronomy techniques. So scientific techniques, there's a lot of data reduction there. And I'm not going to lie, I do a lot of scaffolding. So in this, I'm going to try to play this. I don't know if it'll get recorded, but I'm trying. So hopefully everybody could hear that. That was me in a YouTube video for my students explaining what that line of code did. And I referred to the fact that this data cube from the Pandas data science project labeled the first row as 0, which any computer scientist immediately recognizes. But anyway, so quite frankly, being able to use Google Drive, being able to use GitHub and YouTube made me able to scaffold these activities, these remote coding activities. And so far it's been a success. And I wanted to share a little bit about that. So I can't prove this yet, but I think this model is going to help equity, gender equity, race equity, socioeconomic status equity. I really do think that's true. And so I asked my students to give me some feedback on the first one of these we did. And hopefully you can see that most people found it pretty darn fun. So you can see it was enjoyable. Actually, it was a lot of fun. That's a lot of people from my class, from this group. And then I asked them to compare this to other activities. How difficult was this? And it looked like either I did too much scaffolding or just the right amount, but it looks like it was, there. It's a work in progress, like all educational projects. But this was some feedback that I think this general astronomy class in my high school, which has got a real slice of the whole school. I have every ethnic group, and males and females, and in between males and females, and this is everybody. It's not like my AP computer science. I mean, my AP physics class, which is mainly white and Asian, with only a few Latinos and Black students. This is a little bit of everybody. So astronomy is a place where I can really use computing to affect a larger crowd. So I want to say thank you to those people who are bothering to watch this after the fact. At least, I see at least somebody's here. I think Astra may be in the room with me. I hope so. But I if I were seeing this talk, I would want these labs. So there's a GitHub repository where you can go and fork my projects and have at them. I have a link there to the project homepage with a lot more information about how I did this. And then each of those links you see there, cluster distance with photometry and the equivalent width with spectroscopy and the Hubble's law with SDSS galaxies. These are labs I'm actually doing in my classes. As a matter of fact, the equivalent width with spectroscopy I'm going to be doing next week. There are a few others I've made, but I'm making them up as I go. These three have been kind of vetted by scientists. They've looked at them and said, hey, these aren't terrible. So I just would welcome everybody to go, or encourage you to go to my website, check out the stuff that's there. And, thank you guys for listening, especially considering that Astra, who's here with me, is my only attendee. And I'm hearing her in the chat. She's saying Alice can't get in. Yeah, I noticed, Astra, that I'm going to try to turn my camera on now that I'm nearly done. And hopefully you can see me. Yeah, I noticed that the Digital Divas and Texas CSTA links, even though I guess I kind of assumed anybody doing one would do both, or be able to do both, but clearly not. So I'm going to make Alice watch this later. So Astra, oh, you got 2 logins. Oh, okay. Yeah, I wonder if Alice didn't notice. But anyway, I'm hoping you got something to ask me, because I'm going to put you on the spot, Astra, as I'm in this recording. I feel like coding, one for Digital Divas and for this, yeah. I feel like this using coding in science class is a way to really make a science class more accessible. You can use project-based learning. And the thing is, if you're really interested in equity in your science class, we have to do things differently. Instead of the rote memorization and the lecturing and the preparing for the AP and IB exam, letting people get their hands on things. I feel like PBL, open inquiry, that sort of thing, this really lends itself to it. And I was wondering if you thought that too, that maybe coding might be an avenue to actually try to make equity happen. You got any thoughts on that? Type them in the chat if you can. I might be able to let you talk, but I don't know. Yes, I'm a fan of using real data with coding to make connections with students. Well, I hope I'm doing that. And as a fellow HISD employee, I'm hoping that maybe you and me and some other computer science educators can look at this sort of thing, and we can make some model lessons for other teachers to use. And because what I'm trying to do here is give people a starting point. They can take everything I've written and rip it apart, use the parts that are good and build their own and put it back together. So I hope that it's on the recording now, Astra, so now we got to do it. But you, me, Alice, virtual learning might give us the flexibility. Yeah, that's, you know what? Even if it's not virtual learning, I think that is exactly what we need to be doing. I think you're really hitting on something across campuses. Students from my school, students from your school, meeting on Teams, talking about a project they want to do, something small, and just trying to do it and see how far we get with it. I think that's a great idea, and hopefully we're going to be able to pull that off. Let's see. I think we're supposed to end at 40. Astra, do you know off the top of your head, as my only attendee, whether or not, I think we end at 40 and not 45. I think that's right. So do you have anything you wanted to ask me? Yeah, you're looking at the agenda, but while you're doing that, if there's something you wanted to, ask me, let me know. Part of me wants to feel embarrassed that no one came to my talk but Astra, but I really don't care. I like doing it, and I'm so glad I had someone I know show up. And I know Alice wanted to, so yeah, I don't really mind. It's funny. Yeah, it's time. Okay, so unless you have something for me, Astra, I do want to give you an opportunity. If there's something you wanted to ask me specifically about what I'm doing, I'd love to answer it. I also think, while you're thinking of something, that, I teach astronomy. No one else is teaching astronomy in HISD. This might be a way to get some of that content between groups. So that would be cool. All right, it's 40. So I'm going to go ahead and end, because I want you to be able to go to your next thing. I'm not quite sure how to do that. But thank you for coming, Astra. Thanks for showing up. I really appreciate it. Can we share concepts in my CS classes with your data? 100%. I have live data that's ready to go, and it's yours. So I'll send you an email. We'll talk. All right. Thank you, Astra, for coming. And for those watching in the future, thanks for watching. and enjoy the rest of your conference. Bye, everybody.